When we look up at the night sky, we see a tapestry of silence and light, a static backdrop that seems eternal and unchanging. But this tranquility is an illusion. For every point of light is a raging nuclear furnace caught in a desperate battle against its own gravity. These are the stars, the architects of the cosmos, the engines that drive the evolution of the universe and forge the very atoms that make up our bodies. Before we embark on this journey through cosmic time to understand our stellar origins, please take a moment to like this video and subscribe to the channel for more explorations of the universe. To understand the life of a star, we must first comprehend the scale on which these celestial giants operate, a scale where human history is but a fleeting blink. Stars are not merely bright objects. They are massive spheres of plasma held together by their own immense gravity, burning for millions or even billions of years. They act as the fundamental processing plants of the cosmos, taking the simplest materials created in the Big Bang and transmuting them into complexity. Without stars, the universe would be a cold, dark, and boring expanse of hydrogen and helium gas, devoid of solid ground, water, or life. The story of every star begins not with fire, but with coldness, deep within the vast, towering structures we call nebulae. These stellar nurseries are colossal clouds of gas and dust stretching for light years across the galaxy, beautiful yet incredibly frigid. Inside these clouds, the material is spread thin, thinner than the best laboratory vacuum on Earth, yet the total mass is staggering. For eons, a nebula may remain peaceful, a sleeping giant waiting for a catalyst to wake it from its slumber. Eventually, something disturbs the peace. Perhaps the shockwave from a nearby supernova, or the collision of two galactic clouds. This disturbance creates regions of slightly higher density, where gravity suddenly gains the upper hand over the internal pressure of the gas. Once gravity takes hold, a runaway collapse begins. The gas falls inward, clumping together and drawing in more material from the surrounding cloud. As the cloud collapses, it begins to spin, conserving angular momentum, flattening into a rotating disk with a dense core at the center. Deep inside this core, the pressure mounts, and the friction of colliding atoms generates immense heat, creating a protostar. The protostar glows with heat energy, but it is not yet a true star. It is merely a collapsing ball of gas trying to find equilibrium. This phase can last for millions of years as the object grows hotter and denser, crushing the atoms in its center closer together. Finally, the core temperature reaches a critical threshold, about 10 million degrees Kelvin, where a profound transformation occurs. At this temperature, hydrogen nuclei move so fast that they overcome their natural repulsion and fuse together to form helium. This process, nuclear fusion, releases a tremendous amount of energy, creating an outward pressure that halts the gravitational collapse. A star is born, entering the longest and most stable period of its life, known to astronomers as the main sequence. It is rare for a star to be born alone. They usually form in clusters, hundreds or thousands of siblings emerging from the same nebula. Over time, the gravitational ties of the cluster loosen, and the stars drift apart to chart their own solitary courses through the galaxy. The life that awaits each new star is predetermined by a single factor: its mass, or how much material it managed to gather during its formation. Mass drives everything. It dictates how bright the star will shine, what color it will be, and ultimately, how it will die. Let us look at the vast majority of stars, the red dwarfs, which are much smaller and cooler than our own sun. These small stars burn their fuel with incredible efficiency, sipping at their hydrogen reserves so slowly that they can live for trillions of years. Because the universe is only 13.8 billion years old, no red dwarf has ever died. They are the silent witnesses of cosmic history. Moving up the scale, we find stars like our Sun, medium-mass yellow dwarfs that strike a balance between longevity and luminosity. Inside the Sun, 600 million tons of hydrogen are fused into helium every single second, releasing energy that eventually reaches Earth as sunlight. This delicate equilibrium between the crushing force of gravity and the explosive force of fusion maintains the star's shape for roughly 10 billion years. But at the top of the hierarchy are the massive stars, the blue giants and supergiants, which live fast and die young. Because of their immense gravity, they must burn fuel at a voracious rate to keep from collapsing, resulting in temperatures that shine with a blinding blue-white light. While a star like the Sun lives for billions of years, a massive star may exhaust its fuel in only a few million, a mere heartbeat in cosmic time. Regardless of mass, the main sequence is a period of stability, a time when the star provides a steady source of energy to any planets orbiting it. But hydrogen, the fuel of the stars, is not infinite, and eventually the tank begins to run dry. When the hydrogen in the core is depleted, the nuclear fires dim, and the outward pressure that held gravity at bay begins to falter. Gravity instantly wins the tug of war, crushing the core inward, which paradoxically raises the temperature even higher than before. This new heat ignites a shell of hydrogen around the core, causing the outer layers of the star to expand drastically outward. The star transforms into a red giant, a bloated, cooler version of its former self, consuming everything in its immediate vicinity. In about 5 billion years, our own sun will undergo this transformation, expanding to swallow Mercury, Venus, and possibly Earth. Deep inside the red giant, the core continues to shrink and heat up until it reaches 100 million degrees, hot enough to fuse helium. The fusion of helium creates carbon and oxygen, the fundamental building blocks of organic life, forging them in the heart of a dying star. For low-mass stars like the Sun, this is the end of the line. They cannot generate enough heat to fuse carbon. The outer layers drift away gently into space, creating a beautiful glowing shell of ionized gas known as a planetary nebula. Despite the name, these have nothing to do with planets. They are the colorful ghosts of stars, creating some of the most stunning sights in the universe. Left behind at the center is the exposed core, a white dwarf, a hot, dense sphere about the size of Earth but with the mass of a sun. A white dwarf is a stellar corpse, no longer performing fusion, slowly cooling down over billions of years until it fades into darkness. But for massive stars, the story is far more violent and complex. Their death throes shape the chemistry of the entire galaxy. These giants have enough mass to crush their cores beyond helium fusion, continuing to fuse heavier and heavier elements. Carbon fuses into neon, neon into magnesium, magnesium into silicon, and so on. With each stage happening faster than the last, the star becomes a layered onion of elements, a factory creating the periodic table under extreme pressure. But this alchemy hits a dead end when the core begins to create iron. Fusing iron does not release energy, it consumes it. The moment iron is formed, the star has signed its death warrant. With no energy output to push back against gravity, the balance that held the star up for millions of years vanishes in an instant. In a fraction of a second, the iron core, roughly the size of Earth, collapses inward at 25% the speed of light. The collapse stops only when the neutrons are packed so tightly they physically touch, transforming the core into a neutron star. The infalling outer layers slam into this super hard core and bounce off with unimaginable force, triggering a supernova. A supernova is one of the most energetic events in the universe, momentarily outshining the entire galaxy of hundreds of billions of stars. In the chaos of this explosion, the heat and pressure are so intense that nucleosynthesis goes into overdrive. This is where the heavy elements are born. Gold, silver, platinum, uranium, forged in the fires of stellar death. Without supernovae, these precious elements would not exist. The gold in your jewelry was created in the dying breath of a massive star. When the dust settles, two types of remnants can remain, depending on the original mass of the star. If the core is between 1.4 and 3 times the mass of the Sun, it remains a neutron star, an object of mind-bending density. A neutron star packs the mass of a sun into a sphere only 20 kilometers across, roughly the size of a city like Manhattan. A single teaspoon of neutron star material would weigh 1 billion tons, as much as Mount Everest. These stars often spin hundreds of times per second, becoming pulsars, the cosmic lighthouses that sweep beams of radiation across the galaxy. But if the remnant core is heavier than 3 solar masses, not even the density of neutrons can stop the collapse. Gravity crushes the matter into a single point of infinite density, puncturing the fabric of space-time itself. A black hole is formed, a region where gravity is so strong that not even light can escape its grasp. The boundary of no return is called the event horizon, a dark sphere masking the singularity within, where our understanding of physics breaks down. While black holes are often seen as destructors, they, like neutron stars, are simply the final evolutionary stage of the most majestic stars. However, the death of a star is not just an ending. It is the necessary beginning for everything that comes after. The debris from these explosions, the clouds of hydrogen, helium, carbon, oxygen, and iron drifts through the interstellar void. This material enriches the galaxy, increasing its metallicity and providing the raw ingredients for the next generation of stars. When a new nebula collapses to form a star, it now contains these heavier elements, the ashes of its ancestors. This is crucial because you cannot build a rocky planet like Earth out of just hydrogen and helium. You need silicon for the rocks, iron for the core, and oxygen for the water and atmosphere. Around our young sun, 4.6 billion years ago, these heavy elements clumped together in the protoplanetary disk. Dust grains became pebbles, pebbles became boulders, and boulders became planets, eventually giving rise to the Earth. And on this third rock from the sun, something extraordinary happened. The complex chemistry of the stars evolved into biology. Every atom of carbon in our DNA, every atom of calcium in our bones, and every atom of iron in our blood was created inside a star. We are literally made of star stuff. We are the universe observing itself, a collection of atoms that has gained consciousness. The cycle continues even now. In the Orion Nebula, new stars are igniting at this very moment. And somewhere in the galaxy, an old giant is taking its final breath, seeding the void with the potential for future worlds. Understanding stellar evolution gives us a profound connection to the cosmos. We are not separate from the universe, we are a part of its ongoing flow. Let us return to the details of this process to explore the specific mechanics that allow these miracles to occur. Consider the immense timescales of the main sequence again. It is a period of deceptively calm stability. During this time, the star is a self-regulating thermostat. If the core gets too hot, it expands and cools. If it gets too cool, it contracts and heats up. This hydrostatic equilibrium is the secret to why life can exist on Earth. The Sun has remained relatively stable for 4 billion years. However, stability is not eternal. The accumulation of helium ash in the core is the ticking clock of stellar mortality. As the core becomes clogged with helium, the hydrogen fusion is pushed outward into a shell, making the star burn fiercer. This luminosity increase is why the Sun is 30% brighter today than it was when the Earth formed. In another billion years, this brightening will likely boil off Earth's oceans long before the red giant phase even begins. The red giant phase itself creates winds that blow the star's atmosphere into space, stripping away mass. For massive stars, these winds are like hurricanes, creating Wolf-Rayet stars, unstable beasts that have blown off their outer hydrogen entirely. These stars are exposed cores, burning at incredible temperatures, destined to explode at any moment. When we talk about the death of massive stars, we must also consider the role of binary systems. Many massive stars have a partner. If one explodes, it can kick the other across the galaxy or strip its atmosphere. Sometimes, a white dwarf can steal material from a companion until it reaches a critical mass limit known as the Chandrasekhar limit. When it crosses this line, the white dwarf detonates entirely in a Type 1a supernova, leaving nothing behind. These explosions are so consistent in brightness that astronomers use them as standard candles to measure the size of the universe. But the core collapse supernovae of single massive stars are the true engines of creation. During the collapse, the core reaches temperatures of billions of degrees, allowing for the rapid capture of neutrons. This R process builds elements far heavier than iron, filling out the bottom rows of the periodic table. Recent discoveries suggest that the collision of two neutron stars, a kilonova, is also a major source of these heavy elements. A kilonova can produce 10 times the mass of the Earth in pure gold in a single second.
These events are rare, but over the history of the universe, they have salted the cosmos with precious metals.
The remnants of these explosions, the nebulae, are not just shapeless clouds. They are structured by magnetic fields and shock waves. Some remnants, like the Veil Nebula, appear as delicate, twisted filaments of gas, expanding for thousands of years. As these remnants expand, they eventually mix with the interstellar medium, the diffuse gas between stars. This enrichment process means that every generation of stars is chemically different from the last. The very first stars, population 3 stars, were massive, pure hydrogen monsters with no planets. They lived fast, died hard, and began the cycle of enrichment that eventually led to population I stars like our Sun. It is sobering to realize that we live in a chemically matured universe, one that has had time to brew the ingredients for life. But what of the ultimate fate of these stellar remnants, the white dwarfs, neutron stars, and black holes? White dwarfs will cool until they become black dwarfs, cold, dark, crystal spheres floating in the void. However, the universe is not yet old enough for a single black dwarf to exist. The cooling process takes longer than the current age of the cosmos. Neutron stars will spin down and cool, eventually becoming dark, silent relics of their former glory. Black holes will eventually evaporate through Hawking radiation, though this takes googles of years. The era of stars is fleeting. We are lucky to live in the stelliferous era, the time when the universe is lit by fusion. In the distant future, star formation will cease as the available gas is used up or flung into intergalactic space. Galaxies will grow redder and dimmer as the bright blue massive stars die out, leaving only the long-lived red dwarfs. But let us pull back from the far future to the present, to the wonder of the process as it happens now. The recycling of matter is efficient but not perfect. Some matter is locked away forever in black holes or brown dwarfs. Brown dwarfs are the failed stars, objects that didn't have quite enough mass to ignite hydrogen fusion. They bridge the gap between gas giant planets and stars, simmering with deuterium fusion but never fully shining. Every object in the sky tells a story of mass, gravity, and time. And the most important chapter of that story, for us, is the formation of the Goldilocks zone. A star must be stable enough and long-lived enough for life to evolve on its planets. Too much ultraviolet radiation from a blue giant would sterilize a planet. Too little from a red dwarf might freeze it. Our Sun is, in many ways, the perfect host star. Not too violent, not too dim, and with a long, stable lifespan. But even the Sun has a life cycle that dictates our ultimate fate. Long after humanity is gone or has moved to the stars, the Sun will end its main sequence journey. Its death will destroy the inner solar system, but the material it ejects could become part of a new star system. Perhaps, billions of years from now, atoms that were once part of Earth will be in the body of an alien creature under a new sun. This idea of cosmic recycling is central to modern astronomy. Nothing is wasted, everything is transformed. The iron in your blood was forged in a supernova.
The calcium in your teeth came from a dying giant.
The oxygen you breathe was created by helium fusion. We are intimately connected to the life cycles of the stars. When we study the stars, we are not just studying distant lights. We are studying our own genealogy. The universe is a grand, evolving organism, and stars are its metabolism. From the cold, dark nebulae to the fiery crucibles of supernovae, the process is driven by the simple laws of physics acting on a massive scale. As we continue to observe the cosmos with telescopes like Hubble and James Webb, we refine this story. We find new anomalies, new types of stars, and new mysteries. But the fundamental arc remains the same: birth, life, death, and rebirth. A cycle written in light and gravity across the canvas of the void. The next time you look up at the stars, remember that you are looking at the furnaces that forged you. You are a child of the cosmos, a brief spark of consciousness in a universe of burning giants. Thank you for joining us on this journey through the life cycles of the stars.